Hello, Algebra 2 students. Today we're going to be taking a little bit of a closer look at that equation that we started to mess with the other day for all of the quadratics. Okay, so today's title is Properties of Conic Sections. And our objective for the day is to learn to identify characteristics of quadratic equations that lead to various conic sections. As always, press pause anytime you need more time to copy something down, and then hit play when you're ready to move on, especially since some of our drawings here the last day or two have been a little bit more complicated. Okay. Now, the last time, you already have this in your notes. You don't have to copy this down. Okay, but we looked at the basic conic sections and how they were physically generated by passing a plane through a double-napped cone at various angles. The one on the left was when you pass the cone through the pass the plane through the cone such that it's perpendicular to the main axis. Okay, the next one to the left is the same idea, plane passing through the cone but not perpendicular to the main axis. Okay, the second from the right, passing the plane through the cone such that it is parallel to an exterior side of the cone, and then on the right, passing the plane through such that it is parallel to the main axis of the cone. And we learned that the four cross sections that were generated by this intersection between the plane and the double-napped cone were the circle, the ellipse, the parabola, and the hyperbola. Okay, so then we looked at this equation. Okay, the general quadratic equation in two variables was ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. A, b, c, d, e, and f are constants. Okay, but as I said last time, don't get frightened of the equation. It's not going to have all of these terms activated in it all at once. Different types of conic sections are going to have different um, types of resulting graphs. Now, your assignment from last time had you playing around with some of the graphs of the circles and ellipses and parabolas and hyperbolas and stuff like that. Okay, so begin copying here. Okay, we started to see in that assignment what the different variations of that formula would cause in a graph. I gave you four equations in the assignment, and you had to plug in values for x and find the corresponding values for y. And when you transferred all that information into the graph, hopefully you discovered your four different conic sections. Okay, so hopefully what you noticed in retrospect would be this. Okay, we saw on those equations some of them had matching coefficients and some of them had different coefficients. That's going to be important when it comes down to the different types of conic sections. We also saw some of the equations were sums of terms and some of them were differences of terms. And again, that's going to be important to the different types of conic sections. We also saw some equations that had variables in matching dimensions, meaning maybe x was squared and y was squared, things like that. And we saw sometimes where we had variables in varying dimensions, meaning maybe x was in the second dimension, y was in the first dimension, x squared and y to the first, stuff like that. And again, that's going to be important to the conic sections. Okay, so where we are at now is we need to learn to tell the differences in the graphs by just seeing the equations alone. And that should be a common a common theme that we've kind of had all this semester. Our main focus has been trying to understand when you change an equation, what does that do to the graph? And when you change a graph, what does that do to the equation? Okay, so that's kind of where we're going to start with the conic sections. Okay, so here we go. As you've seen for years now, If an equation allows A, B, and C all to become 0, now A and B and C, we're talking about the three coefficients from the quadratic, that is the ax squared, the bxy, and the cy squared. If all three of A, B, and C are 0, we end up with something similar to this guy, 4x to the first plus 2y to the first plus 5 equals 0. And the summary of an equation like that would be that all of our variables are in the first dimension, x to the first, y to the first. Okay, and we've seen equations like this one for years because this is our friend, the line. This is a linear equation. When x is to the first and y is to the first, you have a linear equation. Okay. Now, let's look at what happens when we start to activate some of the A, B, and C terms. Okay, this time let's activate A. We will allow the coefficients of B and C to be 0, but A is now going to become part of the problem. Okay, when that happens, we end up with equations that may look like these two guys. Okay, you can see in the first one we have an x squared, but only a y to the first. In the second one, we also have an x squared, but only a y to the first. Okay, and of course, we're just talking about the degree of these variables, the highest exponent that the variable has to offer. Okay, and when this happens, when you have kind of a dimension mismatch there, one variable in the second dimension, one variable in the first dimension, hopefully you remember, okay, so one variable in the first and one variable in the second, okay, hopefully you remember this is our friend, the parabola. Okay, we spent a couple of months working on the quadratic equations and the graphs that they generate. Okay, so there's our friend the parabola from back in December and January. We've seen him plenty, spent a lot of time working on the equation, how to factor it, how to run it through the quadratic formula, how to solve it, all that good stuff. Okay, so let's look at a different possibility, different combination of the A, B, and C terms. Let's say this time B is a 0, the B term is a 0, but A and C, whatever they are equal. Okay, so this time we're going to have the x squared and the y squared both participating in our equation. The xy term is not to be found at this point. Okay, but in both of these equations you can see that the degree of each variable is 2. Okay, we have x squared and y squared in both cases. So when that happens, this is going to produce our circle. Okay, x is squared, y is squared, and the coefficients both match. We have positive 1x squared, positive 1y squared, and it could be any value. You could have 5x squareds and 5y squareds. The point is they are both squared and the coefficients match. That's going to be your circle. Okay, another situation we might run into is this one. Our coefficient b is still going to be 0. A and C are still active in the problem. Okay, they have the same sign, but not the same value. Okay, so that is to say that there will be an x squared term, there will be a y squared term. They will both either be positive or both be negative. Okay, and their coefficients will be different from each other. Okay, so here's a possible example for a situation like that. We have an x squared, we have a y squared. They are both positive, but one is a 4 and one is a 3. So the coefficients match the sign, but do not match the value. When you do this, you have caused an ellipse. Okay, we will get into the how and why of these equations here before long. Right now, we're just trying to identify them when we see them. And there's only one type of conic section left, so I'm sure you know what it's going to be, but let's look at the equation anyway. Okay, B, our B coefficient is still a 0. A and C are still both participating in the equation. Okay, this time the A and C term are going to carry different signs. Now, the coefficient on this one is not actually important other than the fact that the signs are different. So x squared and y squared, one of them should be positive, one of them should be negative, exactly like that equation you're looking at now. We have an x squared, we have a y squared. Their signs are different. Okay, so one has a 4 coefficient, one has a 3 coefficient, but that's not really what's being looked at right now. It's just the fact that their signs are different. And when this happens, you have discovered our friend the hyperbola. Okay, now one thing to take note of is that for all 4 of these equations, all 4 of these cross sections, conic sections, pardon me, we have had one particular aspect, one particular detail that has been the same for all of them. Some of them used x squared, some of them only used x to the first, some of them used y squared, some of them only used y to the first. Some of them had coefficients that matched, some of them did not. Some of them had signs that matched, some of them did not. But all of them failed to have one thing, and that was that none of them had a b term. Okay, the b value was always zeroed out, so the xy term never showed up in any of the equations. And that is going to be the truth. That's going to be the way that we are going to leave it. But let me go ahead and introduce you to the why behind that. What happens if the b term is not a 0? That would bring the xy term into the equation, but what kind of an effect would that have on the graph? Okay. Now, the xy term cannot change the very nature of the graph. A circle is still going to be a circle by the definition that we just saw of a circle. An ellipse is still going to be an ellipse by the definition that we just saw of the equation of an ellipse, and so on. Okay, so the xy term cannot change the type of graph. However, it does play with the orientation of the graph, and that means that the axes that hold the conic section in the graph, that has been changed. So it's almost like taking the xy coordinate plane and rotating it, okay, in the graph. Okay, so you can hardly see this. I apologize, the colors are conflicting a little bit. Okay, but what we're looking at there in the green that you can hardly see is an ellipse that is in our graph. Okay, whatever its equation is doing, that's fine. The point is its b value is a 0. It has no xy term. Okay. However, if we were to activate that b term, make it something other than 0, it's possible we might see something like this. And I apologize again, it's kind of hard to see. Okay, but the ellipse is in there, and you can see that it has been rotated in the graph somewhat. Well, the b term is actually what is responsible for that. Okay, so we are not going to be dealing with the b term in our equations too much. Okay, but do file it away in the back of your head that this is what the b term does. Okay, so a quick rundown again real quick. In summary, we wind up with the unit conic sections. Okay, unit conic sections is the term that is used to describe shapes with their centers that are at the origin and have not been expanded or collapsed really in any way. Okay, so we don't have any crazy coefficients or HK values going on in our conic sections. These are just the basics. So you probably want to scribble these down all in one place so you can have them for reference. Okay, so there's our 4 conic sections: circle, ellipse, parabola, and hyperbola. Okay, here is the basic format for the equation of a circle. Okay, Now, there may be other terms that are in it, and we will get to that later, but the basic equation is x squared plus y squared equals r squared. Okay. Now, we haven't dealt a whole lot with things like r in our equation, but based upon your travels in geometry and your understanding of a circle, I think everybody well knows r represents the circle's radius. Okay. Now, the ellipse. Okay. An ellipse is nothing more than a stretched out circle. It has been pulled one direction or the other. Okay, so we should expect to see basically the same type of formula with x squared and y squared, but we have the possibility of some coefficients going on with x and y. Okay, so this is the way that the equation is formatted, actually with m in the denominator and n in the denominator. It may not always show up that way in the equation or the questions that we work on, but this is the way that the formula is written. Okay, so as m and n change, okay, obviously that changes the coefficient of x and y, and those changes are going to cause our circle to stretch or collapse in one direction or the other, or both. Okay, the parabola we should be well familiar with. Our basic parent parabola, y equals x squared. And of course, parabolas can travel in any direction in the graph, okay, up, down, left, or right. So the variables can be transposed. It's not always going to be y to the first and x squared. Could very easily be x to the first and y squared. And lastly, our hyperbola is a little bit harder to write the basic equation out because of the possible sign changes. Okay, but expect that you will have an x squared and a y squared. Expect that one of them will be positive and one of them will be negative. But the important information with the hyperbola is that they have opposite signed coefficients. So if the x wants to be positive, then the y must be negative. If the x wants to be negative, then the y must be positive. Okay, so that is your basic information on the properties of conic sections. A lot of our work from here on out through the rest of the unit is going to be working these equations, examining what changes do what things to the graph, how the graphs can be translated back into equations, and so on. Okay, so that is it. I appreciate you finding time to get your notes taken care of, and I'll see you in class.